G'day, good evening. Thank you for listening. This is a medical show. I respect the law and I hope you do too. The information provided today is for educational and scientific purposes. The information is fact-checked and any of the papers or websites that have been discussed will be put in the description below. Today's topic, it's probably going to be soil phosphorus and soil potassium for plant nutrition. It's week 3 in a course called Soil Fertility and Fertilizers, which was written in 2022. It's one of the better courses that I've done at university, and I'm just going through that when there's really no questions or discussion topics from chat. It's been a bit slow of late, so that's why I've gone down this route. So if you're watching back, just fast forward to probably some slides and that'll be the start of it. Good indication of when it is. I'd guess to say that that's what's going to be, but who knows? So I'll give it till 2 minutes to wait to see if anyone arrives and puts up any topics, which is another 35 seconds. Excuse me. Another 30 seconds now. Looks like it's going to be it. I just give it a little bit of time because it takes there's a 30-second delay between when somebody writes and when I get something when I see it. Oh, up to 30 seconds anyway. That's why I'll give it up to a couple of minutes, which is right now. 2 minutes has happened. All right, let's get started on I'll share the screen. This is an excellent, one of the most relevant and on-point courses that I've done to date. So this is the course that I'm going through, and it's these slides here for this course, and it's week 3. Anyway, this is what it is. So let's start. Let's see, chat, there's one person now, I think. I don't think there's anything being written yet. No worries. All right, open this and it starts. Oh, okay, just got a massive delay for some reason. Phosphorus. So phosphorus has generally 3 forms, but it's only one form that's really relevant for the purposes of our plants, because it's to do with the pH. So one's really an acidic form and one's a more around alkaline form. That summarizes that topic. Plants absorb phosphorus in the 2 forms. So that's pH dependent. There's 3 replaceable protons, hydrogen ions of H3PO4 combined with calcium to form 3 different combined salts of calcium and phosphorus, resulting in different classes of phosphatic fertilizer. The functions of phosphorus is found in plants as nucleic acids, phospholipids, coenzyme NADP and NADPH, ADP, and other compounds. So if you were to get your plant material for organics, you would know that the minerals are bound up. So that means they're immobilized in the plant material or organic matter. And this is how we would get phosphorus. So you'd hope that this is retained, all the enzymes, the protein, and other compounds, so that you can extract them later on and use them once the microbes break it down. Heavy concentration of phosphorus is found in the meristematic regions of actively growing plants, where it is involved in the synthesis of nuclear proteins, because that's meristematic regions where it keeps dividing, and there's a few of them on the plant, a few of them areas in the plants, and yeah, that's why, because it keeps producing them from functions of phosphorus. Important for cell division, and development of new tissue. Phosphorus is also associated with complex energy transformations in the plant. Adding phosphorus to soil, low in available phosphorus, see that good word, available. Phosphorus promotes root growth and winter hardiness. It stimulates tillering and often hastens maturity. Phosphorus cycle, not really going to go through that because this course goes into extreme in-depth. So this is the phosphorus cycle, how it goes. It cycles. How does it break down? Where does it come from? Is it immobilized or mineralized? Because microbes have already unlocked the immobilized phosphorus. Except, I won't go through all that. You can see it's quite detailed, and up the top is the components. Oh, sorry, I can't even read that. I'll keep going because there's a lot more relevant. Well, this is pretty relevant, but it's especially for organics, it is very relevant because you want to know where to get phosphorus to be there to break down later on to be available for the plant. So rock starts out as phosphorus cycle. So when it rains, phosphates are removed from the rocks and are spread out through the soils and water. The plants uptake these phosphate ions from the soil. Phosphate moves from plants to animals, where herbivores eat plants and carnivores eat plants and herbivores. Animals release the phosphate into the ground. It's then decomposed. It goes through the cycles, and as the rocks are forming, they will either join with phosphate or the phosphate will go into the roots of the plants and start the cycle over again. Phosphorus absorption and desorption. So where does it get absorbed into and what sort of factors are affecting it, like the soil mineral type, the amount of clay, temperature, because with temperature, the phosphorus absorption increases as temperature increases. So that's pretty cool to know. And flooding the soil reduces phosphorus absorption. So if the plant's too wet, don't expect much, or the substrate's too wet, sorry. Forms of phosphorus in the soil. Not really going to go into great detail here, because as you can see, it's probably quite confusing for you. And if it's not, I'm sorry, I'm not going to go through it. Organic phosphates. The organic phosphates in soils are derived secondary by addition of organic matter to the soil through the growth of plants and decomposition of plant residues. Kind of what a lot of the studies are related to organics, and organics is my topic. I don't like the mineralized fertilizers because I like organics, and that's the way that I promote. Microorganisms synthesize organic phosphate compounds because they might have phosphatase that they would release as the microbe, and then that would break down the phosphates, making it available to the soil and uptake to plant tissue. The organic phosphates constitute of 20 to 90% of total soil P. Mineral soils containing less and peaty soils under the pasture contain more. So the organic phosphates constitute to 20 to 90% of the total P in the soil. And the nature of about 62% of soil organic P is still there after a crop. So there's a lot is retained there because you remember from before how it's bound up in all of that nucleic DNA components. So each cell has a lot of these components. So any cells that you find from the plant material are going to be high in phosphorus. Forms, already been through that. But this course, it just really heavily goes into detail and just drums it in. It's a shame we've only got an hour because we could go on, but I'm not going to. Calcium phosphates, remember it was bound up? So these are the different forms. Quite high tech. Monocalcium phosphate monohydrate. And there's a few other ones there that are very long. Combined with iron and aluminium is not good, because that's going to bound up your cation exchange, and too much iron isn't good. In the initial stages of acidic weathering, phosphate becomes increasingly bound to iron and aluminium ions, releasing the silicate minerals by replacing the OH- from the hydroxyl minerals or oxygen from the oxide minerals. So these are the two forms of ferrous phosphate. Has been detected in water-logged or poorly drained waters, and in profiles having fluctuating water and air regimes. Aluminium phosphates have also been detected in the sand and silt fraction of some soils. That's not good. You don't want that one. Because remember, the cation exchange, very important. You don't want that in the soils to bind it up. In the presence of excessive potassium and ammonium ions, the alkali phosphates of iron and aluminium give rise to leucophosphate, ternochrite, and myelite. All right, I can fast forward a bit. Soil phosphorus, origin and nature. Soil phosphorus, exists in many primary and secondary compounds. So where is it bound up? So the primary minerals, about 95% is more in the soil phosphorus. The random inclusion of phosphorus in silicate minerals like zircon occurs during the phosphorus of crystallization. Phosphorus deficiency symptoms are generally dark to blue-green or to blue-purple leaves, if you see them very dark. Plants lacking in phosphorus may develop dead or necrotic areas on leaves, petioles, or the fruits. Similar to nitrogen, phosphorus deficiency may cause premature leaf fall or purple or red anthocyanin pigmentation. There you go. A couple of good examples. In a rapeseed plant, a tomato plant, see how it's just really, really dark? You think, wow, that's so healthy, it's so dark. No, that's actually phosphorus toxicity. Not good. And more than likely, you'd be fertilizing and it would be trying to get it out of the substrate, which would already have a lot in it, phosphorus already. So that's probably how it happens. There's a good little depiction of it. But it's a shame it's in cartoon and not really in colour. But I'm not going to go through them all because I think that little summary earlier was enough for the phosphorus deficiencies. Darkening, you think, well, the anthocyanins are so good, but it's not. It's phosphorus because it's the darky colour. And the causes, how do you get a phosphorus deficiency? Cold weather, excessive rainfall, acidic soil compaction, injury from herbivores, pressure from insects, or poor soil health. And they'll go through all of these, the surface runoff just washes it all off, leaches it out. Leaching is the downward movement of water along the soil profile. So too much overwatering. It's hard outdoors to control things sometimes. That's why the farmers, 95% of the lower 48 is polluted groundwater in here for this reason, because there's so many mineralized components like phosphorus and nitrogen that are fed to the surface and washed out and leached out, percolates down and contaminates, because down the groundwater it's got nowhere to go. Well, it flows, of course, but that's its sort of end point. The subsurface, no, the effect of pH on the availability, kind of talked about that, but this goes into detail, so I'm not going to go into that much detail. Here's the two different forms of it, so you can see with the pH. What's this one? The effect of pH on phosphorus availability. Well, it's leached, from the That's a better one, because it's got the H2PO4 minus and then the HPO4 2 minus. So this is the one that you want. This is the form, as you can see. It's more readily available between the 4 to the 6.5, and this is really only available from the 7.5 upwards. So H2PO4 minus. That was actually an exam question. Effective fertilizer play. I should see if anyone's arrived. Oh yeah, Sunshine's arrived. Hello, Sunshine. RB. Nice to see you, mate. Just going through phosphorus if you come in late. Phosphorus and potassium. So the effective fertilizer placement. So since P is quite immobile within the soil profile, fertilizer placement close to the seed can increase the availability to the crop. Placement outside of the root zone decreases efficient use of phosphorus unless roots grow extensively out to where it has been placed. So ensuring the placement close to the root while avoiding the seed burn is necessary to enhance availability to the crop throughout the season. The effect of organic matter on phosphorus availability. This is my area I like. So over time, the phosphorus that attached to the organic matter can be displaced by organic anions from the soil solution, effectively increasing P availability to plants' roots for uptake. Organic matter can also coat and interfere with P binding sites, making P more available for uptake by plant roots. Phosphorus that is already tied up within soil organic matter and mobilized, it can be mineralized throughout the season and will act as the source of phosphorus available for the crop. Phosphorus mobilization. Second down, so the phosphorus acquired by plants through bacteria and fungus is 75%. So if you try to not run, if you poison your substrate, if you use H2, the sodium, the peroxide, hydrogen peroxide, things like that in your substrate for other things, well, consider this fact. Total phosphorus acquired by plants through bacteria and fungus is 75%. That's a lot. Biochemical process operating in the rhizosphere determine the mobilization and acquisition of soil nutrients. Mobilization mechanisms and microbes. So organic P mobilization can be direct or indirect. So it lowers the pH. It has flow-on effects. And oh yeah, aspergillus. There's some P mobilizing microbes as well down the bottom. That's the genres. They're not the species. So you might want to include some of those in your beneficials if you're getting phosphorus deficient results. Well, actually, you want to include them anyway. I use a few of them just in case. It doesn't hurt, because the plant can work symbiotically with these to ask for it when it needs sometimes too. Phosphorus fertilizers, rock phosphates, other types too. The largest deposit of phosphorus fertilizers is in Morocco, followed by the USA. And you have to be careful of adulterations if you're getting it. Most down the bottom, most conventional phosphorus fertilizers are made by reacting rock phosphates with sulfuric acid to produce phosphoric acid. The phosphoric acid is then further processed to create many of the most common phosphorus fertilizers. Flowchart on how they manufacture it. I'm not going to go through it. Manufacturing process. Flowchart for manufacturing it. with different fertilizers. So you get a different end result by putting in different things, and that's what it's called. H3PO4, flow chart for making that one. Remember the two different types, and this is its classification in common industry. You can see the end result of phosphorus, 32, 46, 58. So 50% of the triple superphosphate, TSP, it contains phosphorus. So 50%. So there is available in large forms if you really want. But the one down here at the bottom, rock phosphate, bone meal, raw meal, look at those content, 20 to 25%. So that's the inputs for phosphate I support. Raw bone meal, bone meal. General probabilities, no. Phosphorus fertilizer, super. And then it goes into each one. So we'll wait until we go to the, no, it doesn't say it. Phosphorus fertilizers, no. The effects of phosphorus in the soil, no. It goes into a lot of detail. Factors affecting its management. Well, you either got a, that was a good flow chart of its management, because there's all different ways it can be put in and taken out. Yeah, manure, good way to put it in, 70% phosphorus. Because it's all microbes, and all the microbes in the poo are all the DNA, which contain all those phospholipids. And DNA material has phosphorus as a backbone. Comparative fertilizer values, no. They do make good points, but I've still got to go through potassium yet. You can read that if you really want to get into it, because here's potassium. I should stop and see if there's any questions. No, that's okay. Because potassium is one of the essential major plant elements after nitrogen and phosphorus. Makes up just under 1%. It's 0.5%. Its management is important due to its hard to get. Potassium is the most abundant macronutrient in the soil. It is the 7th most common element in the lithosphere, which contains on the average 2.6% potassium. Potassium present in soils, more than 98% occurs in primary and secondary minerals. Potassium is associated with the movement of water, nutrients, and carbohydrates in plant tissue. It's involved with enzymes in energy production, and also helps regulate the opening and closing of stomata. There's some of the roles it does. That was just explained before, but this goes into a bit more detail. The role of potassium in plant growth. Well, it increases root growth and improves drought resistance, maintains turgor, reduces water loss and wilting, aids in photosynthesis and food formation, reduces respiration and preventing energy loss, enhances translocation of sugars and starch, produces grain rich in starch, increases plant protein, builds cellulose and reduces lodging, and helps retard crop diseases. And this is a bit more detail on it. That's a good way to see plant potassium deficiency, is the scorching of the leaves and the burning appearance on the leaf margins, on the tips. So right on the edges of the leaves, you'll see it'll be dead. Only a little tiny bit. You'll think, oh, wow, that's so little tiny. It's maybe it's saline problems that I got, salinity. But it's not. If you look at the leaf a little bit better, you'll see, actually, I'll just wait until I go up further, because that's not a good example. Because it's like not, you see the greening in the middle and the edges is a very good, there you go. The greening in the middle and the edges is very yellow. This is early stages of potassium deficiency. And then at later stages, it'll start and go into the plant a little bit more, and then these leaf margins at the tips here, they die. So you just see little dead bits. That's potassium deficiency. See there, it's starting to die off. Necrotic cells are forming, dead tissue. Here's a good comparison with nitrogen. So you can see it's the opposite of nitrogen. So nitrogen has the vein up the axis where it's gone from all its chlorophyll, where potassium is still green. This is on a corn plant, I think, but it's similar on each leaf of every plant. Very similar. So your phosphate, this is good to summarize the three. Phosphate is the darkening, way too dark, deficiency. Potassium is the dead margins at the edges. And nitrogen is an overall yellowing, and more so down the main mid-axis, mid-rib, it's called. Factors affecting potassium fixation. So the charge, density of clay, extent of wedge zone. Wedge zone is higher amounts where potassium fixed. Solution concentration and nature of concentration of other cations. Remember of the cation exchange in its value, its bonding capacity for cations. Potassium cycle, relatively simple. It's like everything else, it can be leached out. Actually, you can see there, I'm not really going to go through it. It's just a very straightforward one. Add your inputs, take your X's out, keep it cycling around. This is a more in-depth one, which shows you inputs, how you can get it from plant residue. Mineral fertilizers, no. Or immobilized fertilizers, yes, bound up in manures and other rich phosphorus rock, bone meal, DNA compound, like, anyway. The leaching, runoff, okay, that'll do for that bit. Soil plus solution is more fixed minerals bound up in the clay. Oh, it's isomorphic substitution within the clay particles. Not going to go on about that though. Original source of K, potassium, is primary nutrients in micas or potassium feldspar. Feldspar is one of the most common soils in the world. Potassium is released in its cycle. Okay, good. Factors affecting potassium availability. Types of soil colludes. So you want 2:1, so it's exchangeable. That's to do with clay. Wetting and drying of soils, freezing and thawing affect potassium, and soil pH. High pH increases the fixation of potassium because of the less protons or hydrogen atoms and aluminium at the exchange sites. Forms of potassium readily available. Mineral, non-exchangeable. Sorry, I'm trying to summarize this as I read it to think if it's relevant to talk about. I don't think it is much relevant. I mean, everything's relevant, but am I going to go into that much detail? The other, which I'm not. I just want to skim over these because this is it's 1 week of lectures. I'm trying to summarize into 1 hour, which is you don't know what's 1 week's of lectures worth. I think the lecture's about 45 minutes on to an hour, and get 5 of them. So 4 to 5 hours worth of lectures, trying to summarize into 1 hour. And forms of K removed. Oh, that's okay. Exchangeable, that sort of relates to the previous ones. Primary minerals, unavailable K. Depending on the soil type, approximately 90 to 98% of total soil potassium is found in this form. So it's bound up and unavailable. That's why microbes are so important, like Bacillus mucilaginosus. That's a potassium-releasing microbe, and if you put them in that microbe with feldspar or micas, you'll find that it will release it. Bang, you've got heaps of it. So that's an organic process that could be followed. Secondary minerals and compounds are slowly available. So the forms of potassium is trapped between layers of clay and is frequently referred to as being fixed because it's going to be isomorphic substitution, so it's going to be exchanged with another cation before it can be swapped out. Readily available K is dissolved in water, or it could be held in clay particles and exchange sites which are found in the surface of clay particles. And the potassium is attracted to the clay. Exchange sites is more available for plants that the potassium trapped between layers of clay minerals. Factors affecting plant potassium uptake. Soil moisture. So high soil moisture usually means greater potassium availability. Increasing soil moisture increases potassium's movement to plant roots and enhances its availability. That's why drip feeding is really good. So if you've got a cultivar that's potassium pig, you might want to consider doing your irrigation that way. Soil aeration is another factor affecting plant potassium uptake. The soil aeration and oxygen level. I won't read that. Another thing is soil temperature, which is pretty important because the optimum soil temperature for the uptake of the potassium, plant potassium, is 60 to 80 F. Potassium uptake reduces at low soil temperatures. And for those few that are in English, 60 is about 20 Celsius, and that's about 28 Celsius. Or actually, that's 18. Common potassium fertilizer sources. No, not going to talk about them because I don't think you should be using that way. I think you should be putting in the effort and doing it organically. So these are mineralized fertilizers, and no, I would like a immobilized fertilizer to be broken down by microbes. And only reason I support these types is for foliar deficiencies. So if you have, you can fix deficiencies quite easily by foliar spray, as long as it's not calcium, boron, or manganese, which is the immobile elements. Common potassium fertilizer sources. Nope. But this is going to go through potassium nitrate. You can see the solubility in grams per litre on the y-axis to water temperature. And potassium nitrate, actually I don't want to discuss these, but it does have an effect. Temperature to solubility, see it slowly uprising. Manure down the bottom. The potassium content of manure varies with animal type, the feed, rations, storage and handling practices. So huge, big factor they're differing. Luxury consumption. Luxury consumption occurs, it's when a soil nutrient levels are above the optimum and plants take more of a nutrient that is needed for functioning and production. Potassium is commonly taken up in excess. So what's this say? Potassium content in the plants, availability in the soil or in your substrate. So it's luxury consumption. Potassium mobilization. Potassium is present in a very small amount, ranging from 0.04 to 3%. Despite it being limited, 98% of this is bound up within phyllosilicate structures, and remaining 2% exists in the soil solution or on the exchange sites in clay to become, or on other exchange sites, more so in clay, to become available to plants later on. Hence, soil fertility is decreased due to low availability of this nutrient. Many microbes in the soil are available to solubilize unavailable forms of potassium-bearing minerals, like the micas, feldspars, illite, orthoclasses, by excreting organic acids, which either directly dissolve the rock or chelate it to bring the potassium into solution. K, mobilizing microbes. Oh, look, Bacillus mucilaginosus. And no, I didn't look at these before I read them. Rhizobum, aspergillus. I don't support using aspergillus because you can get the lung disease called aspergillosis. Aspergillus niger, that's very common. So yeah, mucilaginosis, there you go. Burkholderia is a non-symbiotic nitrogen-fixing bacteria too. Rhizobium is only for legumes. Pseudomonas, huh? And that's the genre. That's because that's the species there, mucilaginosus, and that's the genre. So Pseudomonas. I'll look into that. That's it. Any questions? G'day, wrapped up. How you going? G'day, Fred. 420 Fred. How you going? So, anything interesting there that anybody found? It's more so, I can summarize the potassium and phosphorus by deficiency and toxicity. That's the best thing to go off. So you don't need any plant tissue test or any soil test parameters. Just know the symptoms. I'll go through them again. I'll just know the symptoms, and then you can make your decision. So you know for the next run that, all right, I've got to add a little bit more. I've got to release a little bit more because the amount that might have been available in the substrate was high because it was a high amount of manure, but it wasn't available to the plant. So in other words, I need some of those microbes to unlock the potassium that I've put in there, or the phosphorus. Phosphorus is high in manure. That's something that I'd pull out of this discussion that we've gone through. So you can really learn your deficiencies in your plant leaves because they're all similar across all different species and genre. Monocots, dicots, they're all the same. They'll all show that symptom. And then, bang, go from there. Then you know. And that's what is healthy by growing, getting to know the cultivars that you enjoy and that you focus on. So by changing all the time, it allows error to happen, because by knowing the same thing all the time, you can change this next thing. All right, I'll just adjust this. I'll get some Bacillus mucilaginosus and see if that helps. Oh, cool, it did. Okay, it only helped a little bit. Maybe I could add some more. I'll get a higher CF colony forming unit ratio on it. By knowing those things, you can make your own decisions to bring out the genetic potential. Yes. So that was pretty good. That's the summary that I could bring up from that. I've shown the symptoms already. I can go through and show you what next week might be, because if there's going to be no questions. I'll just try and have a look at it. Where is it? No. I'm not sharing the screen either. Okay, I'll share screen. So this is what was done today, week 3. And next week will be week 4. Calcium, magnesium, and secondary nutrients and their role in plant nutrition. So it's similar to what today was like, but just goes through all the secondary nutrients, which is the calcium, magnesium, and sulfur. Hang on for a sec, please. Sorry about that. So that's what I intend for next week to be, was that week 4 in that cool course that I like. I hope you're enjoying it, because I'm enjoying it. It's good to brush up on different things, to get familiar on practices, so it makes easier gardening. That's a good way to put it. So there's no questions coming through. I think it's back to the cricket. Hope everybody's enjoying the cricket. Even though most people in the States, it's only new in the States and in Canada. In Canada, it's been a lot longer. Actually, it's really old. But in the States, it's where most people view this from. It's new, relatively new. And there's actually, like the Seattle Hawks or something, there's different, it's about a dozen teams throughout the 50-odd states that there are that are starting to compete. So it's pretty good. Something you used to get into. Good, peaceful sport with heaps of statistics. Righto. If nothing else to be said, we'll have to leave, and we'll see you all next week. And we'll be going through more nutrients. Then it'll be into the fun. How do we use these nutrients? What can we do? How do we cycle them? All right. Thanks everybody for watching. Happy breeding, happy growing, and good health to you all. Bye-bye.